Hello everyone. In this video, we're going to discuss on assignment 1, questions 1 to 4, and in the order of Lim Yiizamy, Yiizamy, me, and then finally no Atira. So without further ado, I'll pass this over to Lim Yiizamy, who will discuss on question 1.
Hello there, my name is Lim Yiizamy, matrix number 75451. Today I will discuss on question 1. In 1a, chemical structure for the complex is shown in the diagram. Charge for both cyclopentadiene, diol, and chloride ion is -1, while carbonyl is neutral. Therefore, we can calculate the oxidation state of the titanium. The oxidation state of titanium is 3+. For 1b, the chemical structure for the complex is shown in the diagram. Charge for phenyl acetylate ion is -1, while trimethylphosphine is neutral. Therefore, we can calculate the oxidation state of iridium, which is +1. For 1c, chemical structure for the complex is shown in the diagram. Charge for both phenyl acetylene and propene is -1, while ethylene diamine is neutral. We can calculate the oxidation state of the palladium, which is +2. That's all from me. Thank you.
Hello, so I'm going to explain about question 2. So first and foremost, we need PtCl4. Okay, then when we add NH3 into PtCl4, this NH3 will be replacing any of the Cl ligand in the PtCl4. Then when we add another NH3 into the PtCl3 NH3, this NH3 will be replacing this Cl or this Cl, but not this Cl. Okay, why? Because Cl trans to Cl is more labile than Cl trans to NH3. Okay, so this, as you can see, that the NH3 now is cis to each other and Cl is now cis to each other as well. Okay, and then when you add thiourea into the compound, the thiourea will be replacing either this ammonia or this ammonia. Why? Because Cl is more trans than NH3, so meaning that this Cl will kick the NH3 out. Okay, so when you have the thiourea here already, as you can see, I replace it in this place, and then we will be adding NH3 into the compound again, and then since thiourea is trans to Cl is more labile than Cl trans to NH3, so meaning that this Cl will be kicked out. Why? Because thiourea is more trans than Cl. Okay, this thiourea will kick this Cl out and replace with NH3. Okay, once we already have the NH3 here, we will be adding ethylene diamide into the compound, and then because thiourea is much more trans to NH3, and then the meaning that the thiourea trans to NH3 will be more labile compared to Cl trans to NH3. So meaning that this NH3 will be replaced by the ethylene diamide, forming a trigonal bipyramidal complexes. Okay, in this trigonal bipyramidal complexes, the only two ligands that are trans with each other is Cl and NH3, meaning that when we add chloride ion into this coordination compound, the Cl is trans to NH3 and Cl is more trans than NH3, so meaning that this NH3 will be kicked out and replaced by the chloride ion and synthesize this coordination compound. Thank you.
Hello everyone, this is Ivan, and I'll be discussing on question 3, which is to choose the most stable complex from a pair of it. So in the first pair of complex, we can notice that the difference between the two complexes, one is attached to a Shinol ligand, another one is attached to an amino ligand. So the amino ligand is a good donor rather than a good acceptor. So the titanium amino bond will consist of only pi bonding, which makes the structure less stable overall. Whereas the Shinol ligand has an NTP pi orbital at the carbon atom, which will allow back bonding to occur, making this complex more stable than the other. So in the second pair, the difference between these two complexes is that one has alkyne and another has methyl. So the complex that is attached to phenylethyne is more stable because the phenylethyne is an unsaturated ligand. This allows for room for back bonding to occur, whereas the methyl ligand in the other complex is saturated. This does not give them the empty bond required for back bonding, thus it is less stable overall. So that's all from me. I'll pass this on to the next person. Thank you.
Hello, my name is Nur Atira Abdi Alin. I'm holding matrix number 76172. So I'm going to explain the question number 4, which is calculate effective atomic number for the complexes below. For the question A, we have the metal central Au, and the atomic number of Au is 79, and the oxidation number is n plus -1 plus -1 equal to -1 equal to n equal to n plus 1, and the coordination number is 2. By using the formula z minus x plus 2n, we substitute the value, which is 79 minus plus 1 plus 2 times 2 equal to 82 electrons. So for question B, the metal central atom for the complex is IR. So the atomic number of IR is 77. The oxidation number is n plus 2 negative times with -1 plus -1 equal to 0. So we get the n equal to +3. The coordination number is 6. So by using the formula, we substitute the value 77 minus +3 plus 2 times 6 equal to 86 electrons.